In this video, we'll be talking about gradient descent, the key optimization algorithm used in machine learning. By the end of this video, you'll understand the basics of gradient descent and how it works. Let's dive in. Imagine you're a hiker trying to find the lowest point in a valley. You can only see a small area around you, and you want to descend the mountain as efficiently as possible. Gradient descent is a lot like that. In machine learning, we often need to find the optimal values for a model's parameters to minimize a cost function, which represents the difference between the model's predictions and the actual data. Gradient descent is an iterative optimization algorithm that helps us find the minimum of this cost function. Before we dive into how gradient descent works, let's first explore the concept of gradient. A gradient is a mathematical concept that refers to the rate of change of a function with respect to its variables, which is known as the slope of the function. In other terms, it's a derivative of a function that has more than one input variable. In calculus, the gradient of a function is represented by a vector that points in the direction of the steepest increase of the function, and its magnitude represents the rate of change in that direction. The gradient is often used in optimization problems, where the goal is to find the maximum or minimum value of a function, by iteratively adjusting the input variables in the direction of the negative gradient until a minimum or maximum is reached. Consider a blindfolded individual who wishes to ascend a hill with the fewest number of steps possible. He might begin climbing the hill by making really large steps in the direction that is the steepest, which he is allowed to do as long as he is not very close to the summit. Yet in order to prevent overshooting it, he will take fewer and smaller steps as he approaches the top. The gradient can be used to mathematically describe this process. Assume that the graphic depicts our hill from the top down, and the red arrows represent the climber's footholds. Consider a gradient in this context as a vector that specifies the length and direction of the steepest step the blindfolded man can take. It should be noted that the gradient from x0 to x1 is significantly longer than the gradient from x3 to x4. This is because the vector's length is affected less by the hill's steepness or slope. Due to the fact that the hill becomes less steep as it is climbed higher, this nicely illustrates the example of the hill. Therefore, a reduced gradient goes along with a reduced slope and a reduced step size for the hill climber. Instead of climbing up a hill, think of gradient descent as hiking down to the bottom of a valley. This equation describes what the gradient descent algorithm does. D is the next position of our climber, while A represents his current position. The minus sign refers to the minimization part of the gradient descent algorithm. The gamma in the middle is a weighting factor, and the gradient term is simply the direction of the steepest descent. The main idea behind gradient descent is that, at any point on the cost function curve, the gradient, or slope, points in the direction of the steepest increase. By taking small steps in the opposite direction of the gradient, we can iteratively move towards the minimum of the curve. There are three main types of gradient descent, each with its own trade-offs. Batch gradient descent. This method calculates the gradient using the entire dataset. It's computationally expensive but provides a stable and accurate estimate of the gradient. And the way it's done is that we evaluate the cost function at an arbitrary point and with a process called backpropagation. We can evaluate the negative gradient of this cost function and take a small step in the direction. Gradient descent continues in an iterative fashion. It computes the negative gradient at a new point, takes a step in the direction, and so on. Stochastic gradient descent, SGD. In contrast, SGD calculates the gradient using a single data point at each step. This makes it much faster but introduces noise into the gradient estimate, which can cause the algorithm to jump around. Mini-batch gradient descent, a compromise between the two. Mini-batch gradient descent calculates the gradient using a small subset of the dataset. This strikes a balance between computational efficiency and gradient accuracy. The learning rate is a crucial hyperparameter in gradient descent. If the learning rate is too small, the algorithm will make very slow progress towards the minimum. On the other hand, if the learning rate is too large, the algorithm may overshoot the minimum and fail to converge or even diverge. Finding the right learning rate often requires trial and error or more advanced techniques like adaptive learning rates. Gradient descent faces some challenges, such as local minima. The algorithm can get stuck in local minima, which are suboptimal points in the cost function. Saddle points. These are points where the gradient is zero, but they're not minima. Gradient descent can become very slow near saddle points. Highly non-convex functions. In some cases, the cost function can have a complex landscape, making it difficult for gradient descent to find the global minimum. There are various techniques to address these challenges. One important technique is momentum. Momentum is a variant of gradient descent that incorporates information from the previous weight updates to help the algorithm converge more quickly to the optimal solution. Momentum adds a term to the weight update that is proportional to the running average of the past gradients, allowing the algorithm to move more quickly in the direction of the optimal solution. This technique adds a velocity term to the gradient update, helping the algorithm overcome local minima and saddle points faster. Gradient descent is just one of the many tools in the machine learning toolbox, but it is a powerful one that helps us find the best solution to complex problems.